Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study lecture on measurement of 3D geometry. As usual, before we enter the study of today's lecture, let me give you a quick review or overview about the answer to these four basic questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? Question number four, how to learn the knowledge in this course. All right, so let me begin with the answer to the first question, which is about why to study this course. By now, you should know that our mission on Earth include, number one, to understand the world. Number two, to improve or to change the world. Then how to understand the world? The answer is to discover knowledge. Then how to discover knowledge? The answer is to make use of sensory data. Then how to obtain sensory data? The answer is to make use of measurement and the sensing system. All right. Then how to improve the world? The answer is to invent smart machines, smart products, smart system. Then how to invent smart machines, smart product, and the smart system? The answer is to incorporate feedback control, look into the design of these smart products, smart machine, and the smart system. Then what is closed loop feedback control system? The answer is it is a system which consists of three basic modules or three basic blocks. One of them is a sensor. Now you see this course is extremely important. All right. And this slide also shows you that in future, you may see the presence of smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, smart healthcare system, and also Internet of Things in future city. Then what is Internet of Things? Inside Internet of Things, there are two basic devices. One of them is sensor, right? The second question that you may have in mind is about how to study this course. My recommendation to you is to put yourself into the mindset of a designer. Then in this way, automatically you will raise these four questions. Who are the user? What are the need of this user? What should be the functionality of your product, of your system that you are going to develop in order to meet the need of your user? Then what should be the solution behind the design of your product or your system in terms of a sensor or Internet of Sensor, etc. Right? So the answer to question number one should be obvious to you because the user include ourselves and the smart product, smart machine, and the smart system. Then answer to the question number two should be also obvious to you because all these users have the common need, which is to have sensory data, right? Then answer to question number three depends on the nature of the user. For example, smart vehicle may need to have a certain type of sensor, and the smart home may need to have another type of a sensor, etc. Right? So then answer to question number four is to study well this course. At the end of the study of this course, you will know the solution behind the design of your product, of your system in terms of a sensor or measurement and the sensing system. All right? This course. Basically, this course will cover the study of the basic principle behind the design of a popular sensor in electric domain, mechanic domain, environmental system, and the intelligence system. In addition, this course will teach you the basic detail about the physical world, the basic detail about the conceptual world, and also teach you the basic knowledge for you to cope with randomness in the physical world and to understand fuzziness in the conceptual world. All right. Then the fourth question that you may have in mind is about how to learn the knowledge from this course. And basically, you will learn the knowledge from this course in order to guide the design of measurement and the sensing system. And the design of measurement and the sensing system involve two steps. Step number one is to transform the value on the measurement into readable value. Step number two is to calibrate your measurement and the sensing system. The calibration will allow the output to be exactly equal to the input, and the unit of the measurement assigned to the output will be the same as the unit of the measurement of physical quantity on the measurement. All right. Then for step number one, basically you may face these two situations. The first situation corresponds to the case in which it is good enough for you to make use of front-end sensing element to transform the value on the measurement into readable value. However, in most cases, you may face the second situation in which you have to make use of a series of at least two sensing elements in order to transform the value of a physical quantity on the measurement into readable value. All right, so this slide basically showing you the guideline for you to learn the knowledge from this course. All right, so now we are ready to move on to study the measurement of 3D geometry. And this animation basically showing you the use of result of 3D geometry to interact with the virtual scene, right? And today you may heard of this password, meta, right? Meta basically is a virtual world or virtual environment. So a real person is able to interact with the virtual scene as long as we can capture 3D geometry, all right? So you see this application now, right? So now we want to know, okay, a little bit physics behind 3D geometry, and then we need to study a little bit the mathematics, okay, behind 3D geometry. Then our focus is to on the the measurement principle, which allow us to design vision system, okay, or extend the lecture on the measurement of a visual signal into the situation in which we are able to determine 3D geometry, right? So then we need to know what is 3D geometry, then how to make use of a digital image in order to recover, okay, the XYZ coordinate of a point in a three-dimensional space, all right? So you remember we have studied the lecture on measurement of a visual signal. Then visual signal basically is a light ray. So light ray have a source and have a receiver and have a path, right? So receiver basically is an electronic camera, okay? So the output from camera should be a matrix of digital point, right? Image point. Okay, so then we want to know, okay, how to determine or measure, okay, the point source of all these light rays, okay? And in the previous lecture, we have considered the situation in which all the point source of a light ray remain in a two-dimensional space. Then we know how to calculate the XY coordinate of all these the point source of a light ray from image index coordinate. All right. Now we move on to the second situation in which all the power source of a light ray, okay, remain inside a three-dimensional space, but not okay, just in a two-dimensional space. Then in this case, we need to know how to determine the X, Y, Z coordinate of these the point source of a light ray, okay, from the index coordinate of the image. If we know the index coordinate of the image, how to calculate the X, Y, Z coordinate of a point source of a light ray. Now you see the problem. So this lecture basically is an extension of a lecture on the measurement of a visual signal, and also the extension of the lecture on the measurement of a 2D geometry. All right, now we consider the situation of determining XYZ coordinate of a point source of a light ray, right? So first we try to understand, okay, what is a geometry. Then you can relate the description of 3D geometry to the problem of point source of a light ray, because in a three-dimensional space, as long as this is a visible scene, then we can consider all the light ray coming from the point source, all right, in a three-dimensional space. That's it. Then from a digital image, we should be able to calculate XYZ coordinate of these point source of a light ray, all right? Okay, so then you may want to know, why do we need to know this 3D geometry? The answer is very simple. Without the visual signal, human being will have a tremendous difficulty to see each other, and we will have a tremendous difficulty to interact among ourselves. If there's no light, we see nothing, then we will live inside the total darkness. Then our life is not enjoyable, right? So you understand? Visual signal enable us to perceive or to see each of us, right? And also to see the space, right? And which will enable us to act and interact, right? Then similarly, when we develop a smart robot, then smart robot need to know, okay, the visible 3D geometry in the surrounding of the robot. And here is an example, okay, how to enable this robot to undertake autonomous hand-eye coordination in the three-dimensional space without the human intervention, right? So this is a complete video of hand-eye coordination to be performed by robot. And this is a result that we have done more than 14 years ago. Okay, so it's around the year 2008. So this video done by us, okay, around the year 2008. So you see, we use a two camera. Now here you start to pay attention. How come we need to have a two eye, all right? Is it good enough to have a single eye, right? Then you look around in the animal world. I guess the most animal have a two eye. Then what is the reason, okay, behind this requirement, okay? Then how come robot also need to have a two eye, right, in order to perceive a three-dimensional space, right? Then you see the robot could make use of binocular vision to sense a three-dimensional space. Once we know the 3D geometry of object, then he can plan the arms motion, fingers motion to do this pick and place, right? So fully autonomous without the human intervention, right? And this video show you another requirement under the context of Robot X challenge, right? So the task is to deliver object inside the window, to deliver object inside the tower here through a big window or small window, right? And something can implement a mega arm to put the object inside the window, right? Through the window, inside the tower, or through the big window or small window. Then in this competition, obviously you see there's a need to have a measurement and a sensor system for 3D geometry, right? So Then what is a 3D geometry? Basically, 3D geometry refer to the appearance of a physical entity in a three-dimensional space. And here, 3D geometry refer to the perceivable 3D geometry or visible 3D geometry. All right, for those invisible one, it is out of a context of this course. Okay, so because here we talk about the visual signal or visible visual signal. All right. Then what is a 3D space? A 3D space basically is a space in which we need to have three axes in order to provide the reference for coordinate. Therefore, inside a three-dimensional space, we need to have a three coordinate in order to uniquely determine the position of a physical entity. Okay. This slide is a typical example of in three-dimensional space with a tube, cylinder, sphere, pyramid, and hexagonal prism, and triangular prism, cone, and rectangular prism, etc. Right. So these are the primitive or basic entity in the three-dimensional. And this example also showing you the way how to produce a 2D shape, okay, from a 3D entity, right? So if let's say we do the intersection between a cone and the plane, then the result could be a circle, ellipse, parabola, hyperbola, etc. Right? So this just for you to know, okay, the relationship between 2D geometry and 3D geometry. So we can produce a 2D geometry from 3D geometry, all right? And similarly, for complex 3D geometry, we can, okay, decompose it into simpler 3D geometry, or reversely, with the use of a simpler 3D geometry, we could compose a very complex 3D geometry. For example, we can connect two 3D geometry between point, connect two 3D geometry between curve, and connect two 3D geometry between surfaces. So these are the compositional rule for us to apply in order to create very, very complicated 3D entity, right? This is basically showing you how to obtain this very complicated 3D object. Then we have a connection between line. Line is a kind of a curve, right? And connection between point. So you see two edge connect at this vertex, all right? And the connection between surface, all right? So this object and this object are being connected between two surface, right? Then through the application of this combinational rule, then we should be able to create very, very complicated 3D geometry, all right? So the previous slide basically show you the local appearance of 3D geometry. And normally 3D geometry is not a static object, stay there forever. And we may have a dynamic object, it could move, it changes position and changes orientation. So therefore, 3D geometry also include the spatial location, spatial orientation of a 3D entity, right? So this is like in the case of 2D geometry. And for example, when we move our arm, move our hand, then our hand will pass through spatial location and also change the orientation. And when we run, when we move our body on the go biped walking, our body change position, also change orientation, right? Then in robotics, you know that we have two technical terms to describe the global position and global orientation with respect to the world coordinate system. One is called as the path, another one is called as a trajectory, right? So for all the spatial location without the time constraint, then we name them as a path. Then for spatial location with time constraint, then we name them as a trajectory. So these are the two technical terms for us to describe the motion, okay, of a 3D entity in a three-dimensional space. Then we the change in the three-dimensional space we call as a trajectory, right? And the animation basically showing you that this rope perform a trajectory, okay? Because with the pass, it is not good enough, okay, for control system to perform the pass because we need to know the time constraint, okay? And the reason is because all the motion behavior performed by human being or by machine should be performed in real space and in real time. So therefore, time constraint is necessary. Then from here, you will see when the robot moves his finger, moves his arm. So there is a time constraint there, plus spatial constraint. All right. So that's about the 3D geometry. So basically, it's like in the case of 2D geometry, 3D geometry include local appearance plus global motion, right? Because when you change position, change orientation, so basically means what? There is a motion, all right? So local appearance and global motion, all right? So therefore, now you know, okay, what should be the key parameter which needed in order to describe 3D geometry. So basically type of parameter. One is related to the motion, global motion, and the motion will consist of series of spatial location with a time constraint, right? Then when we add the position and the orientation together, then this information is called as a pose. Now you understand pose refer to the combination of a position and orientation. So actually, orientation is called angular position. So then you can say pose refer to the combination of a linear position and angular position, right? And for local appearance, basically is a shape, okay? So we want to know the distribution of the point on the surface of the object, okay, within the local coordinate system. Then you see as a usual, okay, for every entity, whether this entity is in a 2D space or 3D space or inside the camera or in the image plane, whatever. So for any entity, it is a common practice for us to assign a local coordinate system to it. So therefore, we have a global coordinate system plus a local coordinate system, all right? Then in this way, we just need to study appearance within the local coordinate system and the motion within the global coordinate system. Then you see, okay, so our description will be very, very clear, all right? When we talk about the motion, so we always refer to the global coordinate system. When we talk about the local shape, okay, appearance, then we focus on the description in the local coordinate system. Because when we discuss or study the motion, we don't care about the shape, when the object moves from point A to point B, the appearance of the object does not matter. Let's say you move from point A to point B within 5 seconds, all right? Then the equation of the trajectory has nothing to do with the local appearance, right? So you understand. Then the local appearance has nothing to do with the motion, okay? Today you have this face, then tomorrow in another location, your face more or less will be the same, all right? If the time difference is too short, okay, within 1 day, I don't believe your face will change a lot, right? So in NTU, you have a one face at home, you will have a same face, right? So it means what? The motion has nothing to do with the local appearance. So it makes sense, all right? So this is the background knowledge for you to know, okay? And then the global coordinate system, how to represent position, right? The common practice is use position vector. So this is quite easier. Or we can use the equation which constrain the x coordinate, y coordinate, or constrain x coordinate or z coordinate together. Okay, so these are the common practice for us to describe the position in the global coordinate system. All right. Then if we add in time constraint, then we must individually determine the time function for each coordinate in the global coordinate system, all right? For example, x coordinate, y coordinate, and the z coordinate. Later on, I will show you. The good news is for the change of orientation in the three-dimensional space, actually there's only single variable, okay, which represent the change of orientation. So therefore, for the motion in the three-dimensional space, you just need to have a 4 equation of time, 3 for x, y, z coordinate, 1 for the change of orientation. So it's quite simple. Then in 2-dimensional space, you remember we need the 3 equation for trajectory, 2 for x, y coordinate, and the 1 for the angular position, okay, the rotation angle about the z-axis, okay. So you'll see once we go from 2D to 3D, we just increase 1 equation. That's it. So the complexity is not so big, just A in 1 equation. That's it. All right. So this is for the x, y, z coordinate. Then how to represent orientation in the 3D space? So I just show you result, but this result is very important. Okay. So let's say originally we just imagine that all the local coordinate system are superimposed with the global coordinate system. All right. They are superimposed together. All right. So when there's a change of orientation, then the unit vector, which represent x, y, z axis of the local coordinate system, will change. Initially, unit vector will be 1, 0, 0 for x-axis, 0, 1, 0 for y-axis, and 0, 0, 1 for z-axis. All right. When there's a change of orientation, then the x, y, z axis of the local coordinate system will change. Then the unit vector will have a different value. If we put all the unit vector in this way, first column is a unit vector of x-axis, second column is a unit vector of a y-axis, third column is a unit vector of a z-axis, and here x, y, z are the axis of a local coordinate system. Right? Then in this case, this matrix represents the orientation of the local coordinate system with respect to the global coordinate system. All right. So if we put in the time information, that means at the time t0, then you just imagine all the local coordinate system are superimposed together with the global coordinate system. All right. Then it undergoes the motion, changes orientation, reach the new orientation at the time t. Then this is a rotation motion, okay, for the local coordinate system to change from its orientation at the time t0 to the orientation at the time t. You interpret in this way, then should be good enough already. Okay, for those of you, if you are very weak with motion transformation, then this slide is help you with MATLAB to practice a little bit, then immediately you can verify certain statement. All right. I guess all of you should be very strong with all this transformation, because as for students from mechanical engineering, you should be very, very skillful in making use of SolidWorks. I guess for the course which teach you about the mechanical system design, and this should be the basic knowledge for you to know. Okay? All right, how to understand the transformation between two coordinate systems. All right. So this simple program, you can use MATLAB to practice. So assume before rotation, and you have, let's say, orientation in this way. First rotate about the x-axis, okay, by 90 degrees. It's easier for you to visualize. Then y become vertical, z become horizontal. Then I rotate about the y-axis. Then z will reach x position, and x will become at this position. Then rotate about the z-axis, okay, 90 degrees. Then you see y become horizontal again. Then x become vertical, right? So then these are the sub matrix of rotation. If you time them together, then you have this one. So actually, this is represent orientation of at the time t. You just imagine this is orientation at the time t0. This is orientation at the time t. Then this is a rotation from t0 to t. Then you can verify what is this unit vector, okay, x with respect to the coordinate system when t equal to t0. So you see this one unit vector should be, now you see, okay, basically it's parallel to z-axis. So it means what? This unit vector should be equal to 0, 0, 1. Then you see 0, 0, 1. Correct, John? All right. Then what is the unit vector of this y-axis with respect to the global coordinate system at the t0? Then you see this is pointing toward the negative y-axis. Then it should be 0, negative 1, 0. Then you see 0, negative 1, 0. So you ignore this negative 0 because this is a precision due to the calibration in my lab, right? So negative 0 is 0. Okay, there's no difference. Then for z-axis, you see, then z-axis is parallel to x-axis. So it means the unit vector at the time t, it should be equal to 1, 0, 0. Okay, with respect to the coordinate system at the time t0. So you see it's 1, 0, 0. Correct, John? So this is help you to understand. All right. So once you know this, then okay, you can apply, okay, understand this transformation, okay, because in the previous lecture we have made use of this result. Then this after the construction of this matrix, then you have a better understanding of this result. For example, if let's say we use a camera frame or coordinate system to serve as a global coordinate system, because we are camera-centric journal, and our body carry our eye, so we are our body-centric. We are not the the 3D environment-centric journal, because when we move around, okay, if let's say we travel 10 kilometers, then we already forgotten the global coordinate system at the present time, and we always carry our eye. So it's always good to be camera-centric, okay, coordinate system. That means this is our eye, all right? Then if let's say we know for whatever reason, all right, the unit vector of the global coordinate system with respect to our eye, all right, then okay, this is the unit vector of an x-axis with respect to our eye, unit vector of a y-axis of the global coordinate system with respect to our eye. This is the unit vector of a z-axis of the global coordinate system with respect to our eye. And this is the position vector, okay, of the global coordinate system with respect to our eye. Position vector means the vector from the origin of the global coordinate system to our camera coordinate system or our eyes coordinate system. All right. Once you know this, then it's easier. If they say give you any point in this three-dimensional space, and for whatever reason you know its position with respect to the global coordinate system. So this is x, y, z with respect to the reference coordinate system. Then how to know the x, y, z coordinate of the same point with respect to our eye? So answer is very straightforward. You do this transformation, this matrix times this x, y, z, then you will get the new x, y, z. Then this new x, y, z are the x, y, z coordinate with respect to our eye. All right. So you understand? Please apply how you understand the physical meaning behind this transformation. All right. So this is background knowledge. Another background knowledge is important for you to know why we can consider rotation in a three-dimensional space as a single variable instead of three. Because normally you may say, I rotate about the x-axis, rotate about the y-axis, rotate about the z-axis in order to get the new orientation. Okay, that is for you to physically visualize the result. But the good news is such a new orientation could be interpreted by an equivalent axis of rotation with the equivalent angle of rotation. Then we just change this angle gradually. Then this is the rotational motion because the equivalent axis of rotation is fixed, okay, between two relative orientation. It never changes. Is this angle change? So it's good news. Then in this case, we just need to determine time function for this equivalent angle of rotation. That's it. Okay. So you see, then how to determine equivalent axis of rotation, equivalent angle of rotation? So here is a formula. If we know the relative rotation between two local coordinate system, okay, now this is a local coordinate system, right? And because this is more general case, because one local coordinate system could be treated as a global coordinate system. Then, okay, done already. That means in general case, we consider two local coordinate system because this cover all situation. You just let the one of them to be the global coordinate system. Done already, all right? So if we know the relative orientation between two local coordinate systems, all right? Then you use this formula to determine equivalent axis of rotation, equivalent of angle of rotation. So this is finally a total rotated angle. So you can use determine a time function which vary from 0 to this final value, right? You determine the time function. It's like I travel along a straight line, start from 0 until I reach 10 meters. So this is like I rotate from a 0 angle all the way until I reach this angle. Then what should be the time function? So then this is a one-dimensional variable. So it's a straightforward. So you use a polynomial equation of a time function to come out the time function for theta. Done already, right? So then the question is how to determine this one, because this one actually you can relate it R T1 T2 to these two rotation matrix. So you remember for every local coordinate system, we can always talk about its orientation with respect to the global coordinate system at the time T0, right? So time T0. Then for local coordinate system at the time T1 with respect to the global coordinate system at the time T0. So from R T0 to T1, R T0 to T2, you should be able to determine R T1 to T2. So actually it is equal to inverse of this matrix times this matrix. Done already. That means inverse of R T0 T1 times R T0 T2. Done already. Okay. So and physically you can imagine. Okay. So you first determine orientation of R at the T2. Okay, with respect to the orientation to its own orientation at the T0. Then from T0 to T1. Okay, so basically it's from R T0 T2, then times T0 to T1. Then from T1 to T0, then T0 to T1, then T1 to T0. All right. So T1 to T0 is equal to inverse of T0 to T1. So basically it's the inverse of this one times this one is equal to this one. Done already. All right. Okay. So that's about the orientation. Now you know, okay, it is only single variable. So done already. So you know how to represent motion with respect to the global coordinate system. Then how to represent appearance within the local coordinate system. All right, motion needs a representation with respect to the global coordinate system. Then the appearance just need to have a description with respect to the local coordinate system. Then the simplest case is a line, okay? But in three-dimensional space, we need to have two equations to describe the relationship, okay? For among all the points which belong to a straight line, because we need to know the constraint between x, z coordinate and also the constraint between y and the z coordinate. That's it, okay? So this is a representation of a line type. Then here example in the 3D space, for example, we have a line which will pass through point A, point B. Then what should be the equation which describe this straight line in the local coordinate system, right? So then we have equation 1, which relate x to z, equation 2, which relate y to z. And since these two equations will pass through point A, B, then we have these two set of constraint equality. Then we can write these four equations into a matrix form with A, B, C, D as NO. Then you see this is a square matrix. Then we can compute the inverse of this one times this vector will give us A, B, C, D. Done already, right? And how about the circle type of shape in the three-dimensional space? All right, for a circle in a three-dimensional space, it could be treated at the intersection between a sphere and the plane, right? So this is the equation of a sphere. This is the equation of the plane. Then combine these two equations, basically the result will be a circle in a three-dimensional space, all right? Then here is showing you how to the parameter, okay, inside the equation of a circle. And this could be treated as a typical example of doing visual inspection in a three-dimensional space. For example, for whatever reason, vision system are able to tell you XYZ coordinate of point A, XYZ coordinate of point B, XYZ coordinate of point C, and we know ABC is on a circle, right? Now we want to verify whether this circle conform to the design specification or not. Then we need to know what should be the center of this circle and what is the radius of this circle. So therefore, we should be able to come out of these three equations from the equation of a sphere. Then come out of this equation from the equation of a plane in a three-dimensional space. All right. So then we have at least four equations. From these four equations, you see, we need to determine. Actually, we have more than four because this one will contain point A, B, C. So A together, we have 6 equations actually. So then we need to determine A, B, C plus radian and also the XC, YC, and the ZC. So actually, we have 7 equations because point B also on the plane. So for this plane, actually, it will contain 4 equations because A, B, C, D. All right. So in total, we have 7 equations. Then we only have 7 unknown: X, C, Y, C, Z, C, R, A, B, C. That's it. All right. So then we should have enough equation for us to determine all these parameters. All right. So then here is to some guideline for you to follow. So I'm not going to write down all the equations because these are the simple mathematics. All right. First step is to estimate equation of the supporting plane. Right. So then second step is to estimate the center of the circle. Then final step is to estimate radius. So in total, we have 7 parameters to estimate. So how to determine the supporting plane? So you see from this equation, we only have A, B, C, 3 parameters. Then this equation will pass through contain a point A, B, C because we know A, B, C. Then we have enough equation to determine A, B, C. Once we know A, B, C, then we know the supporting plane. Okay. Then we able to determine the X, C, Z. Then how to determine X, C, Y, Z, C, Z, C. So compute the center of the circle. So the hint is here to use the first equation to minus out to subtract with the second equation. Then first equation to subtract the third equation. That means one minus the second one. Then in this way, we will remove XC square, YC square, ZC square, and the R square. All these disappear, all right? Then we only have XC, YC, ZC. Then first equation minus third equation, again, we will remove XC square, YC square, and R square, right? Then because XC, YC, ZC also satisfy this equation, then in total we have 3 equations. 1 from equation 4, and 2 from first equation minus second one, first equation minus third one. So in total we have 3 equations, okay, with the 3 unknown XC, YC, ZC. Then we should be able to solve for XC, YC, ZC because all these 3 equations are linear equations because all the terms with the power of 2 all disappear because we do subtraction. R square disappear, ZC square disappear, XC square disappear, YC square disappear. All right. So you have 3 linear equations. So once you know XC, YC, ZC, the last step is easier. You can use either equation 1, 2, 3 to calculate R done already. All right. So these are the simple procedure for you to follow. All right. Then we continue. Then how to represent curve type of shape in a 3D space? Then we apply this principle. First, we need to have an equation which constrain x, z coordinate. For example, we can use this type of equation. This is a polynomial equation of degree n And then we have another equation which will relate y coordinate to z coordinate. Again, we can use a similar polynomial equation of degree n, right, which relate two variables together. Done already, all right? So then this is a special case, how to represent plane type of a shape. So good news is with this polynomial equation of a degree 1 with respect to xyz coordinate, then it's good enough. Then we have ax plus by plus cz plus d equal to 0. Done already. So this describes a plane in a 3-dimensional space. All right. So then you need to know that the meaning of ABC. Actually, mean ABC put together is a normal vector, which is perpendicular to the plane. Then what is D? D is the distance between the shortest distance between the plane and the origin of the local coordinate system. All right. So these are the meaning for you to remember. All right. Okay. And present space in general in the space. The good news is actually we can use plane, okay, to represent a series of a plane or matrix of a plane to represent any surface in the 3-dimensional space. All right. For example, then we have this matrix of a plane, right, to represent this complicated shape. So then we just need to have this series of simple equations done already, right? And in practice, we can use a rectangular plane or triangular plane. Because triangular plane is easier because 3 points in a 3-dimensional space always determine a plane. But for 4 points, you must make sure these 4 points are coplanar. All right. So then you must pay attention when you use rectangular plane. All right. Make sure the 4 points are coplanar. But with a triangular plane, there's no issue because any 3 points is coplanar in a 3-dimensional space. Right. Why use a rectangular plane? Because this is to reduce the data size. But today, there's no concern for the size of a storage. All right. So actually, we can systematically use a triangular plane, okay? Because we don't care about the storage, because storage today is not the issue, right? But in old day, okay, if you have more data, then storage is an issue. This is why people try to save space of storage. But today, you can ignore such a concern, all right? So, and this slide shows you the example, okay, with the use of rectangular plane to represent all these complicated shapes, all right? Then here is one more example. Then you will see, but to be careful, the representation with rectangular plane may not be good when you represent a surface with a big curvature, okay? When you change the orientation, when the rate change of orientation is very, very large, right? So there is no good representation, all right? Then how's about the use of a systematic triangle? You see a lot of a triangle here. You see, all these are triangle, because with the triangle, there is no issue at all. Only issue is the size of a storage. But today, the memory is very cheap, so you don't care about the size of storage, right? So you care about the precision or realistic. So you see all this rabbit that is inside here, all are triangular. Then here you see all are triangle. You see we get the quite good representation, right? So this just for you to know. Okay, so that's behind 3D geometry and the mathematics behind 3D geometry. Now we talk about the measurement of the 3D geometry, all right? So then you may want to know, why do we need to know the information about the 3D geometry? So actually there are many applications for us to have a 3-dimensional appearance, all right? So in order to have a better interaction or better performance or better execution of the task, for example, okay, for driving, eventually, it's good also for us to know the dimension of the vehicle in front of us, all right? So it's not just good enough for us to know the position. Okay, we may want to know the appearance of the vehicle in front of us, etc. And in particular, if they say we may have a smart shop, when you enter the shop, then this shop knows your dimension then immediately can recommend what's the size of the hair, size of the clothes. If let's say you enter a shop to buy the clothes, to buy the wearable, right? So if the shop know your physical dimension, then immediately it can give you recommendation, John. Then this is a very smart application for you to consider. Okay, so in future city, all the shop will be smart. So when the customer enter the shop, then the shop itself knows the dimension of every customer. Then it can automatically recommend this is the right size for you to choose. Then you see we'll create a surprise. How come you know my size, right? Okay, so this is a typical application. Okay, today not many shops have such a measurement system. Why not you design something? So this could be a project idea for your project. Let's say in Singapore, we may have for every shop, install such a system, then automatically measure the dimension of a passenger, right, or customer which enter the shop, right? In industry, a lot of inspection tasks which may need to know the conformity of geometry and the dimension of the produced part with design specification. So then, therefore, you need to measure the 3D geometry. And this is a case, if let's say all the producer part come in nicely aligned together, then it's easier. Then how about this is a difficult situation? You see, in the conveyor, the producer part may be in all the orientation and the different direction, right? So then it will be difficult, right? So here is just to make you to think about the light ray. Okay, for us, we just consider, the three-dimensional space is a massive matrix of a point source of light. Think this way, okay? So this, you just don't think about the meaningful geometry because later on we can calculate, determine the meaningful data, all right? So at the raw data level, for you, for us, we just imagine a three-dimensional space basically is a matrix, is a massive matrix of a point source of a light. That's it. Then how to determine the XY coordinate of an individual point source of a light. So that is a mathematical problem, behind the measurement of a 3D geometry in this lecture. Very simple, right? Because for us, our camera can capture the light ray. For each light ray, there is a starting point, there is an ending point, and we know the light ray end inside our eye or inside the camera. Then after digitization, we know the index coordinate of image or the light ray, the individual light ray index coordinate. Then the question is, with the knowledge about the index coordinate, how to know the XYZ coordinate of point source of a light? That's it, right? So start thinking this way, right? And for example, if let's say we want to enable robot to undertake the autonomous hand-eye coordination, then the robot must have an eye in order to determine 3D geometry. All right. So there are many reasons, for us to develop a measurement and a sensing system for 3D geometry, which will enable future system, future machine, future product to become as intelligent as a human being. All right. So then what should be the principle for us to measure 3D geometry? So in the previous lecture, we know with a single camera, we can only determine XY coordinate. All right. With a single camera, we can only determine XY coordinate. Then how to determine Z coordinate? Then the solution is what? No choice. We must add in second camera. Then that is a solution. This also explains how come every animal has a two eye. Well, most animal has a two eye, and how come every human being normally we only have a two eye channel, right? So then binocular vision should be the popular setup, not only in the nature but also in industry. So for your vehicle, for your robot, for your smart product, for your smart system, at the least, you must also equip binocular vision to them, right? So then in this way, eventually they could achieve human-like visual intelligence, right? And here also, as I mentioned, okay, so you just imagine all the three-dimensional space consists of a massive matrix of point source of light, because our eye only capture light ray. All right, for each light ray, we want to know what is the start point, what is the ending point, starting point, ending point. For ending point, we know because they will end inside the image plane, right? Then after the digitization, we know the location, okay, index coordinate of the ending point. Then what should be the starting point of the light or point source of a light ray? That is the question. So that is this is the starting point for the light to emit, right? So this is the starting point of the light ray. So single camera not enough, then we use a two camera, then we have enough condition, right? So because image coordinate inside each camera could be related to object coordinate in the three-dimensional space, right? So this is a working principle, right? So then this slide also help you to understand this question: why single camera is not enough? So you remember in the last lecture, we have this equation of a camera's forward projection. So from here, you see, if we know UV, it is not sufficient enough for us to determine X, Y, Z, because there's a short of one equation, right? So this is why single camera not enough. So we need to have a tool, right? So, and then in the nature, most animal has a two eye, right? And the human being also have a two eye, right? So it's interesting for you to know. Then for binocular vision, then what should be the solution? So I directly write down the solution to you, then later on we will show you the proof, okay? So interestingly, the solution for us to calculate X, Y, Z from binocular vision is like this, okay? So A transpose times A, okay, then compute the inverse times A transpose times B. Then what is A? A is this matrix, all right? It's a 4 by 3 because of 1, 2, 3, 4. So we have a 4 row and 1, 2, 3, 3 column. So this is a 4 by 3. This is a 4 by 1, 1, 2, 3, 4. And this ML, this is a projection matrix. This is this matrix B, okay? For left camera, then this is a matrix B for the right camera, left and the right, right? So it's a 3 by 4 matrix. So 3 by 4 matrix. So inside we have a 12 element, right? So this is a solution, all right? Then how to prove this solution, all right? So step 1 of the proof, from the left camera, right? So we have this forward projection equation. Sure not. So this is just this one. It's this one, all right? So this is from left camera. Then we transform a matrix equation into a system of 3 equations, because the first row must equal, the second row must equal, and the third row must equal. Then we have these 3 equations. Then let the first equation to be divided by the third equation in order to cancel the S. Then we expand it, you should be able to get this equation. Then let the second equation to be divided by the third equation in order to cancel the S. Then expand it, then you should be able to obtain this equation. From here, you see we have an equation about the X, Y, Z, another equation about the X, Y, Z. So this is from one camera. So you see, this is not sufficient enough for us to determine X, Y, Z from 2 equations. So there's a short of one condition. Then good news is we have a second eye, right? Second camera. So then we follow the same procedure. This is a forward projection equation. Then we transform a matrix equation into a system of 3 equations. So this is the first row, second row, third row. Then let the first equation divided by third one in order to cancel the S. Then you have this equality. Let the second equation to be divided by third equation in order to cancel out the S. Then you have a second equation. Then here we have another 2 equations about the X, Y, Z. Okay. Now we put together. Then the good news is we have more than enough condition. And actually we have a one extra equation, all right? Then in this case, we can do a least square estimation. So it is kinds of optimization, which will give us a better result, all right? So we have a first two equations from a left camera, second two equations from the right camera. And if we define this is a coefficient matrix, is a 4×3, this vector 4×1, then this system of a 4 equation can be written into this matrix equation. So A is not a square matrix, all right? Then how to transform a matrix, any matrix into a square matrix? Answer is what? Both sides times the transpose of A. Then transpose of A times A become a square matrix, okay? Once this is a square matrix, then we can compute inverse, then both sides times inverse of this matrix, then we get the solution done already, right? So it's very simple. This is the solution. Then next question is, in practice, how to implement the solution. So actually there are different ways to implement this solution. So this is a conventional way, popular way for us to implement it. First, we need to make sure that, let's say, we have a point source of a light at the point Q, which will receive light ray by the left camera here, and then we have a point B, and also received by the right camera here. Then we have a point A. Then how to know point A is correspond to point B, because they come from the same point source of a light. Okay, so this is a problem of feature matching. So here, assume this problem has been solved. Then we can directly proceed to implement this equation already, because we know point B inside the inside the camera come from the point source of the light at the point Q. Then we can directly compute X, Y, Z of the point Q. Done already, right? So this is a popular way for us to think about the implementation. Then, however, you may ask this question, is it easier to do feature matching? The answer is no. Today, this is still open question, okay? Today, there's no general solution, okay? We can solve feature matching in some particular situation, but not in general, right? So, need to do research. Then you may ask this question, what is the best result that we can achieve with respect to the feature matching, or feature matching under the context of binocular vision is called still matching, right? So the best result is to know this constraint called epibolar line, okay? For example, if let's say we have a one point in the left image, then we know, okay, the point source which produce the point on the left camera may come from this line, okay, in space. That means the point source along this line will produce this point, right? Then what should be the corresponding point in the right camera? If let's say the point source is the point P1, then the corresponding point will be here. If the point source is at the P2, then corresponding point will be here. If the point source is at the point here, X, Y, Z, then the corresponding point will be here. So actually, if you link this point together, so then this is a straight line. So it means what? If I give one point in the left camera, I must search the match along this line. And then this line is called as an epibolar line, right? Now, how to determine epibolar line? So it's quite easier, right? So in the three-dimensional space, so you just choose two coordinates. For y coordinate, you choose two values. So it's like to choose a point P1, P2, right? Just set the one coordinate. Then from the UV coordinate in the left camera, you should be able to determine the other two coordinate of a P1, P2, because you know the projection matrix, all right? Then you project X, Y, Z to the right camera, then you get the one point, project this one to the left camera, you get another point, then you link these two points together, okay? So you understand? So basically we apply this equation, all right? So because let's say in the left camera, we know the UV, we have the 1 point. Now we want to find out the where to search for the match in the right camera. So you just choose 2 values for Z, for example, or 2 values for X. Okay, any value like 0, 100, whatever, does not matter. Okay, then use this equation, you should be able to determine YZ. If let's say you want to know, you choose any value for X, then you can calculate YZ. Then you know XYZ. Then once you know XYZ, you apply this equation, XYZ, then you compute UV in the right camera, you get the 1 point, right? Then you choose another value for X, then you calculate YZ. Then you get another XYZ, okay, because you pay attention, this is XYZ with respect to the global coordinate system, right? Then this is the same XYZ coordinate with the global coordinate system. So it's good news to you, Tiana. Once you know XYZ from the left camera, then you apply this equation, you can get the UV inside the right camera. Then you have a 2 UR, VR, then you can link them together, you get the straight line. That's it, that is epipolar line, done already, right? So it's quite easier for you to determine this straight line. So this is a real experiment done by us, okay? More than, I guess it's about 20 years ago, right? So this is inside Robotics Research Center. So let's say we pick up 1 point inside the left image, immediately we can calculate this line. Then we pick up another point here. Then you see this is epipolar line, okay? Computed in this way, done already, right? Then you will see the match to this one actually is on this line, is here. The match to this point, because this is on top of this computer screen. You see at that time, the computer screen is bulky. So it is a proof that this is a picture taken almost 20 years ago, right? Because at that time you see the computer screen is a huge channel, right? So then this point on top of this screen, then you see is here. So you see along this line, all right? So this is a photo taken by us in Robotics Research Center 20 years ago, more than 20 years ago. All right, so this is the best result we know. Then how to solve this problem? By introducing additional constraint. Because with a single line, then we have a lot of candidates. If you have an additional constraint to limit the search, then more or less you should be able to get the exact location. Then you may have heard of Microsoft Kinect, okay, a 3D vision system. So actually, if you project a light, okay, to create a distribution of intensity, then to facilitate the search of the match along this line. Okay, later on we'll show you a little bit of the result. All right. So okay, and another way to overcome this issue is instead of using all the points, then we can use some meaningful data, for example, line segment. Then in this case, you can have exact match, okay, with this epipolar line constraint. So this is a result done by me, okay, more than 20 years ago. So you see, we have a left image, right image, then we just calculate the line segment. So these are the line segment coming from the right image. Then you see the disparity, the gap is quite big. Then we do the match, okay? Then after the matching, then we can calculate the XYZ coordinate. Then this is the 3D geometry computed by still vision. You see, it is accurate, all right? So this is another way to overcome the difficulty of undertaking a still matching or feature matching, okay? So this is a case which make use of meaningful data, all right? And then for some cases, okay, if they say we do not use additional information, so this is the best result you can achieve. Then you see at a certain location, we are not able to do the matching, then we are not able to calculate the XYZ coordinate, okay? So, okay, so then you see we have rough information about the XYZ coordinate. So these are the best results today we can achieve. The left image, right image. Okay, if we project back the color information, so then you see a certain location we miss out some information, right? So, and for outdoor scene, then you see this is okay. cloud of XYZ coordinate, which could be computed, all right? And then for the Microsoft Kinect, basically, he provide a projector, okay, project invisible visual signal, right, into the scene. Then in this way, because the camera can capture all these invisible visual signal, right? Then the distribution of local image is very special. Then you use that information to narrow down the search of a match. Another way is to have a projector. Eventually, you can project a matrix of a visible light, like a dot or grid or something like that. Then in this way, we will facilitate the search of the matching, right? So this is the second way to implement this method, right? Another way to implement this method is to have a ring of a camera on top or in the roof. So for example, in a shop, okay, on the ceiling, you may have a ring of a camera. When the customer enter, then we know the 3D geometry of the body of each customer. Then you can recommend the size of a variable to the customer, right? And if in the outdoor environment, then if you have a flying drone carry the camera, and you have a GPS, okay, you know the very, very precise location. Then this is another way to form this ring of a camera in the sky. Then you can capture the 3D geometry of a building or something like that, right? So this is another way. And this also is very interesting. There's an invention, something like that. So this could be an idea for your project, okay, if you want to work out the detail. So actually we have a single image plane, single lens. Then we have this mirror here, this mirror here. Then we have a triangular prism like this. Then you will see the light ray coming in this direction will be reflected by this mirror, enter the prism. Then due to the refraction, then enter the inner surface of this face, then reflect back to the this second half of the image plane, right? Then you see the image appear here. Then for light ray coming in this direction, okay, reflect by the mirror here and onto this face of the triangular prism. Then due to the refraction, then you enter the prism, then reflect by the inner surface here, then back to this half image plane, okay? Then you will see image appear here. So actually with a single image, then we have a two sub image. And because the light ray for this second half, light ray come from here. So it is equivalent that you place a camera here to capture all the light ray. So then in order to see this image, and that for light ray come in from in this direction, so you produce image here. So this image is equivalent to the image. If you place a camera here, you capture all the light ray, then you get this image. So actually this is equivalent for you to achieve this measurement and the sensing of a visual signal, okay, of a binocular vision or binocular camera, actually with a single camera. So this is a magic invention, John, right? So this is a real result. Then you see, so this is a right image, this is a left image, okay? So actually this is a left half image, right half image, all right? So with a single camera, you achieve this result of a binocular camera or binocular vision system, okay? So, and this is the picture about the real setup, all right? So I guess we should work more in this direction and eventually to improve this result and come out a workable product or workable prototype. So this could be a very good idea of a project for you to undertake, right? So then here are some 3D reconstruction or calculation of XYZ coordinate. You can consider it as a cloud of XYZ coordinate. So you see then the face and the outdoor tree, okay, toy, etc. Right? So it's quite interesting. All right. So that's all about the the study of the measurement of visual signal as well as 2D geometry and 3D geometry. Now we have complete the study of measurement and the sensing system for the two important physical quantity for intelligent system. For example, for human intelligence, we heavily depends on visual signal and the audio signal or sound or acoustic signal. Okay, the number one importance to us should be visual signal. The number two importance to human intelligence should be sound or acoustic signal, right? Then you may want to know what is the difference between these two important or two most important physical quantity to human intelligence as well as to machine intelligence. So this slide is showing you the comparison. For example, for acoustic signal, the frequency is quite low. There is interference, all right? Then the measurement distance is quite short. So we cannot hear someone talk loud if this person is at the distance of 5 meters from you. There's a two person cannot, without the, let's say, microphone or whatever, handphone. Let's say you are standing apart with a distance of 100 meters, for example. It's difficult for you to talk, but it's easier for you to see. So you see, travel distance is short. Reflection is weak. It's not like light. Light can reflect everywhere, all right? And the parameter basically is three: the frequency, amplitude, encoded the text. Because when we talk, and there's information inside the speech, all right? But for visual signal, you see frequency is high, so it's because it's an electromagnetic wave. Interference normally no, okay, it's negligible, all right? Travel distance long, we can see quite far away. Refraction is very strong because when you illuminate a scene, then more or less it's visible to you, okay, due to refraction, all right? Then parameter, we have a frequency, because the color, because of frequency, then we see the color, and the amplitude, because of energy, then we see the luminance, and most importantly is geometry, coordinate. If we have a cloud of X, Y, Z point, then basically it's a geometry, all right? But for acoustic signal is the meaning of speech, is encoded text, right? So this just for you to know, okay? The difference between these two important type of physical quantity for intelligence system, all right? Okay, so that's all for the study of this lecture on the measurement of 3D geometry. The key takeaway for you from this lecture is for you to know the physics behind 3D geometry, mathematics behind 3D geometry, and in particular, okay, the reason for us to use binocular vision in order to determine the XYZ coordinate from index image coordinate. And here, always remember, we consider the XYZ coordinate are the position of a point source of a light ray, because we use a camera to capture the light ray. Then we know the ending point of a light ray, which is inside the image plane. Then we want to know what is the starting point of light ray. So this is why we consider a three-dimensional space as a massive matrix of point source of a light ray, right? Then we know a solution with binocular vision, and we also know a different way for us to implement that solution. And you understand there's still one remaining open problem for us to solve. That is still matching or feature matching. All right, so that's all for the study of this lecture. Thank you for your attention. I'm looking forward to seeing you in the study of next lecture.